Section 10.4 Neural Networks. The perceptron or Adeline or logistic regression is the simplest artificial neuron that makes decisions by weighting of evidence as illustrated in this figure. Obviously, a simple artificial neuron is not a complete model of human decision making. However, they can be used as building blocks for more complex neural networks. See this figure. This complex neural network is made from the simple neurons. So the simple artificial neurons can be used as building blocks for general neural networks. We'll see a simple network to classify handwritten digits using MNIST dataset. The problem of recognizing handwritten digits has two components: segmentation and classification. Once the digits are written, then first we have to segment the digits and we can classify. In this section, we'll focus on algorithmic components for the classification of individual digits. We have public domain data called MNIST dataset available. A modified subset of two datasets collected by NIST, U.S. National Institute of Standards and Technology. Its first part contains 60,000 images for training, 6,000 for each digit, and the second part is 10,000 images for test. For all images, each one is in 28 by 28 grayscale pixels. Look at a simple neural network for the classification of MNIST dataset. 28 by 28 is 784. So for input layer, we have to have 784 neurons. We have one hidden layer. Here pictorially, we have now 15 neurons. For the output layer, we have to have 10 neurons from 0 to 9. This is a simple neural network. For this neural network, the question is, what does the neural network do to get correct predictions? This is an interpretation. Let's concentrate on the first output neuron, the one that is trying to decide whether or not the input digit is a 0. So we try to concentrate on that one. But this one is trying to detect 0 images, and of course it is weighting up evidence from the neurons in hidden layer. So here, another question is, what are those hidden neurons doing? Let's suppose for the sake of argument that the first neuron in the hidden layer may detect whether or not the input image contains that portion. It can do this by heavily weighting the corresponding pixels and lightly weighting the other pixels. So this first hidden neuron is trying to detect that portion of the image. We assume that. And for second one, some other parts, like this one. Similarly, let's suppose that the second, third, and fourth neurons in the hidden layer detects whether or not the input image contains this portion or that portion or this portion. That is an explanation. These four parts together make up a zero image. So if all four of these hidden neurons are firing, then the weighting up will make a conclusion that the digit input images for a zero image. So we can decide in this way. This is an illustration. In fact, the above is a common interpretation for neural networks, but it hardly helps us and the users understand XAI. Neural networks may have been designed ineffectively. And we'll see here later the practical, the performance of this network. Okay, here for the data set, and cost function can be defined in this way. That is now label, and at the last layer, there's activated value, and that must be minimized. Okay, so for weight and bias, and in each iteration, here we try to update, and by using gradient descent method, and that is gradient of the cost function and minus gradient and scaled by epsilon. So it is the formula. Now, however, if we try to get this quantity, that is average value of the gradient for individual points, so that this will be expensive when the number of training data points is very large. An idea to overcome this difficulty is here. We may try to use stochastic gradient descent method. That means we try to use only a part of the data points for an update. And through that, we can speed up the learning. Okay, here we have the stochastic descent gradient method. The idea is to estimate the gradient by computing here that one, and for a small sample of randomly chosen training inputs, by averaging over this small sample, it turns out that we can quickly get a good estimate of the true gradient, and this will help speed up gradient descent. And see here, practically, we'll try to get a small number of randomly chosen training input and M input, and that is called a mini batch. And the average of the gradients from mini batch will be a good approximation of true gradient. And for the classification of handwritten digits for the MNIST dataset, we may choose the patch size is 10, so M can be 10. In practice, you can implement the stochastic gradient descent as follows. For each epoch, shuffle the dataset, and for each m samples selected from the beginning, update the weight and bias using the approximate gradient. Only by using m samples each time it is updated. So each update is counted as an iteration. The epoch means that if you use all the data points, if you go through the whole data set, then we say we finish one epoch. In training, now there are 50,000 points. If you are using, for example, in each iteration 50 points, then to cover whole data set, it requires 1,000 iteration. So after 1,000 iteration, we finish one epoch. Okay. In this way, an epoch and iteration are distinguished. Here is the practical implementation for MNIST digit dataset. Okay, this is done by Michael Nielsen, and here, as you can see here now, there are some explanations. Also, you can see here some of them, but the major part of neural network is implemented in a little bit larger than 100 lines. So we can implement the general neural network within around 100 lines in Python. Python is amazing. You can implement the neural network very flexibly and effectively. Now, we can execute the neural network along with this learning portion. First, we read the data and import the network. That is this one. And here we choose 20 neurons for hidden layer. And this is input layer. 28 by 28 is 784. So we have to choose here 784. And for hidden layer, we choose now 20 neurons. And for output layer, we chose here 10 neurons because it has 10 digits. It must be 10. If we add some integers here, then you can get multi-layer neural network. So we choose only one hidden layer with 20 neurons, but you can make more hidden layers, simply putting some numbers. And so along with this 100 lines of code, you can do it very well organized, and then you can use this code quite easily. Now we define number of epochs. There's a 30. So we'll in the algorithm, it is accessing the whole data set 30 times, and in each iteration, and we are using mini batch, of which the size is 10, and eta, the running rate is 30.0, and by using SGD implemented in this code, here now the stochastic gradient descent method is used to get the trained. Okay. Now, once it is executed, then you see this one. And now start from 0. After finishing one epoch, and we get around 90% of accuracy. After 2 and 91 and become 92 and back to 91 and again 92. That means that it's a little bit oscillatory, and along with this oscillation, now it is gradually approaching, and after 30 epoch, we reach about 94% of accuracy. But it's slow. Even 30 times is accessed through whole data set, and here the accuracy is reached at this one. And each epoch, right now we are using 10 data points, so that to finish one epoch, the number of iteration is now 5,000 iteration. So that after 5,000 iteration, we cover whole data set. That is one epoch. Okay, for this simple network, we have this one. Now, if you are using scikit-learn's support vector machine classifier using the default setting, then you can reach quite similar accuracy, 94%. And if you tune the SVM quite nicely, then you can reach about 98.5%. Now, if we are using deep learning, particularly convolutional neural network, and well tuned, then you can reach at 99.79%. So only 21 images are missed. Here are the handwritten digits. The CNN missed. Can you understand these digits? I believe you cannot understand that. The machine, the CNN, missed only such very odd writing, except that the CNN predicted the right answer. So the performance is close to human equivalent and is arguably better. Even most human cannot get right answer with this accuracy. So it is, I believe, it's better for this handwritten digit recognition. Now, I believe the explainable AI is closely related to neural network design. The above neural network converges very slowly after 30 epoch. Now, you can see here later on, very slowly converging. So it is slow. And we may consider the reason why it is converging slowly. So the question is, can we design a new explainable form of neural network which converges in 2 or 3 epochs to a model showing a better accuracy? That's the question. Because current neural network is not easy to explain, and not easy to explain why it is converging slowly and why it is sometimes oscillatory. It's not easy. But once you can explain the new neural network, then here, because you understand the neural network better, you can get really very fast convergence, and also you can improve the accuracy. And in the machine learning class, I'll deal with some project related with this issue. Okay, that's the end of section. Thank you.